Now we'll talk about assessing the fit of the regression line. On previous pages, we talked about a regression line that can model data that are just a bunch of ordered pairs. But how do statisticians assess the fit of the least squared regression line? When a scatter plot has a linear form, the least squared regression line is the line that best fits the data. However, that does not mean that the regression line is a good fit. It is the best we can do, but it may not still be that great. Statisticians use two different measures to assess the fit of the regression line. First, R squared, the square of the correlation coefficient, or they use standard error of their regression. We use S with a little e for standard error, and R squared for the square of the correlation coefficient. The S with the little subscript e, the standard error of regression, is the standard deviation of the predicted errors. First, we'll talk about R squared. RSQ, or R squared, gives us information about whether we have the right explanatory variable in our linear regression model. A large R squared value tells us that the explanatory variable explains a large proportion of the changes in Y. Our linear model based on X is good at explaining the variability in Y. A small R squared value tells us that changes in X account for a small proportion of the changes in Y. In other words, the linear model based on X is not doing a very good job accounting for the variability we see in Y. This suggests that we should look for another explanatory variable. So here with R squared, R is being squared, so it's no longer that, it used to be that R was between -1 and 1, so R could be 0, R could be 1, R could be -1, or somewhere in between. But now we're squaring it. You multiply a number by itself, it'll never be negative anymore. So now R squared is just something between 0 and 1, I should say. So that's why they're just saying, a small number or a small R squared is doing a bad job of accounting for the variability in Y, and a larger one, a closer to 1, is going to be, it does a good job accounting for the variability in Y. R squared is this formula here, and we can zoom in real quick just to look at it. It's the variation in Y explained by the regression line divided by the total variation in Y. So it kind of measures how closely the variation in the line that we think is modeling the data is to the actual data values themselves. Okay. But we usually interpret R squared as a percentage, but StatCrunch gives it in decimal form. So it's a number between 0 and 1. R squared does not have units, it's just a percentage. Now we'll talk about the other methodology to see how well a line fits the standard error of the regression line. Standard error is the standard deviation of the predicted errors. It is a non-negative number, like all standard deviations. Its units are the units of the Y variable, the response variable. S sub e, or the standard error, is roughly a measure of the average amount that the predicted Y values deviate from the observed Y values, which is an estimate of the average distance that the data points are from the line. In other words, S sub e, the standard error, is roughly the average amount of predicted error for the regression line. For those who like formulas, the standard error is related to the sum of the squared errors. So it's the square root of the sum of the squared errors, which we talked about on a previous page, over n minus 2, the sample size minus 2. Where n is the sample size. Now we'll look at an example where we interpret the R squared and the standard error. Previously, we analyzed the winning Olympic times in the 1,500-meter run for men, X being the years from 1896 to the year 2000. We observed a strong linear form with negative association in the scatter plot. Below is the complete StatCrunch printout for the linear regression model. So they give us this. The dependent variable is time. The independent variable is year. Time is, this is the linear model. Time is 994 point, I'll round it to 19 just for simplicity, minus 0.39 or so here times the year, so Y. That would be your linear model. Y is like your X value, which is confusing. T is your Y value. The sample size is 24. R, the correlation coefficient, would be, this is something StatCrunch calculated, negative 0.89 or so. R squared, if you square that, you get about 0.79, so somewhere in that ballpark. The estimate of standard error or sorry, estimate of error standard deviation is 6.76 about. And they spit out the parameter estimates, okay. The intercept and the slope, okay. The estimated intercept is 994 or thereabouts. The estimated slope is negative 0.39, et cetera, et cetera. Okay, standard error for the intercept, standard error for the slope, the alternative, and the null. Okay, so equal to 0, not equal to 0. Degrees of freedom is 22 because we're looking at n minus 2, and they said n was 24. Just because that's in the denominator of that formula above. It was the square root of blah, blah, blah over n minus 2. The t-statistic here, and then the main thing that matters is the p-value. Both p-values for the intercept and the slope are less than 0.0001, meaning you barely can even detect that there is a p-value. It's so close to 0. Okay, and then they spit out another table. Okay, let's talk about it. The bottom part of this printout below the title parameter estimates contains information that we will not use in this course. So we talked about, we read it out loud, but that's kind of far beyond what we're learning here. Let's focus on the top part of the printout above the parameter estimates. A few notes to connect the StatCrunch printout to familiar concepts. So first, StatCrunch uses the term independent variable instead of the explanatory variable, but they mean the same thing. Y is the independent variable or the explanatory variable, whatever you want to call it, and X is the dependent variable, not independent, but dependent, and it's the response variable. Wait, yeah, okay. The linear regression equation is time equals, that was given above, that they wrote previously, time is actually predicted time. So this model is what we think is going to happen in the future. So it's predicted that this would be when this would happen, but we don't know for sure. We don't have any data values. This is just a model. Sample size 24 tells us that there are 24 data points. We have winning times for 24 years. R, the correlation coefficient, was given in that data table above. It was negative 0.89075356. It's the familiar R value, a measure of the strength and direction of the linear pattern in the data. So R is a negative number. That means it's probably sloping downward. It's fairly close to -1, so it's probably a fairly good model. Now let's interpret the meaning of the R square and the standard error. First, R squared is, if I square that number, yeah, the correlation coefficient R was given here, but then we squared it, or StatCrunch squared it, I should say. I shouldn't take credit for that. And that we can interpret it as 0.79 is the decimal form, but that means 79% of the variability in winning times is explained by chance in the year in the Olympics. In other words, the passage of time is explaining a significant proportion of the improvement in winning times for the men's 1500-meter race. The remaining 21%, which is just 100% minus the 79%, is due to other factors that are not part of our linear regression model, such as improvements in running shoes or more rigorous training regimens, etc. Also, estimate of error standard deviation was 6.7634302. We interpret this as, okay, in StatCrunch, the estimate of error standard deviation is the standard error of the regression. For our linear regression model, the average amount of prediction error is approximately 6.76 seconds. That's what this represents. On average, our predictions from the regression line will have an error of about 6.76 seconds, which means that the Y values, the times, are about 6.76 away from the actual values on average. Too high or too low, they kind of, yeah. It doesn't account for high or low. It just means if they're that far away on average. It doesn't matter what direction, some direction. Now let's look at an example where we interpret the R square and the standard error for a weaker fit. The one above was a stronger fit because R square was 0.79. That's fairly close to 1. It's a lot closer to 1 than it is to 0. Now we'll look at one here. You can kind of tell these data values are fairly scattered. So a lot of them are close to that line, but some are quite a ways away. The least squared regression line is distance equals 576 minus 3 times the age of the person. And we saw this equation before when we talked about viewing distance and the age of the driver. StatCrunch gives an R value of negative 0.793 and a standard error of 51.35. We'll use R square and standard error to assess the fit of the regression line. First, R was negative 0.793. So that means if I square it, r squared is about 0.63. 0.63, which is fairly good, but not as good as the previous example, it was 0.79. You want, the closer you are to 1, the better the relationship is. The linear relationship between age and sign legibility distance accounts for 63% of the variation in sign legibility distance. Other variables besides age account for the remaining percent. 100% minus the 63% would be 37 of the variation in sign legibility distance, such as sign size, letter height, or the contrast between the letters and their background, perhaps. Note that the r-squared value here is smaller, 63%, than the r-squared value for the Olympic data, 79%. This means that this linear regression model does not fit the data as well as the linear regression model for the Olympic data. Now we'll look at the standard error for the regression. Previously, we used the regression equation to predict the sign legibility distance for a 60-year-old driver. The predicted distance was, as we saw above, 576 plus a -3 times the age, so 60. And if you multiply that out and add them together, you get 396. How good is that prediction? Unfortunately, we don't have a 60-year-old driver in the original data set of 30 drivers, so we cannot determine the predicted error. Instead, we use the standard error as a measurement of average error. StatCrunch gives standard error was about 51.35 feet as the average amount of predicted error. Based on that SE, or standard error for the data, we estimate that our prediction of 396 feet has an error of about 51.35 feet. So it could be anywhere from the 396 that was predicted. I could add what is that average error, or subtract it. Anywhere between those two values is where I can expect it to lie, even though I don't have a data value necessarily for a 60-year-old. Note that the standard error value here is larger, 51.35, than the standard error value for the Olympic data. If you scroll up, it was only 6.76. This is further evidence that the linear regression model does not fit the data as well as the regression model for the Olympic data. Because in the Olympic data, yeah, they said that the standard error was 6.76. That means the average data point is 6.76 units away from the predicted one that was predicted by the line, the linear regression model. But that was for the Olympics. But for this example with the driving distance or driving visibility, the standard error was 51.35, which is quite a bit. That's how far away you can expect your average data value to be in terms of the y values away from the predicted one that's on the line. When we compare the two examples, which regression line is a better fit for the data? The regression line for the Olympic data is much better fit than the other line for the viewing distance for drivers, because it has a larger r-squared and a smaller standard error. A larger r-squared value tells us that the regression line accounts for a larger proportion of the variation in y. In other words, the relationship between x and y is doing a better job predicting y. The smaller standard error value tells us that the regression line has smaller predicted errors on average. Smaller error is always better. That means that that's the average amount of units away from the actual values the line is.